Okay, we're back. We are on page 4, I guess, of note 17 of Calc AB. We're talking about accumulation functions and the second fundamental theorem of calculus. I think of those as like two sides of the same coin. I was going to say two coins of the same side, but that doesn't make any sense. So where you see one of them, you'll see the other one, basically. So let's see. We want to find the equation of the tangent line to g of x when x equals 1 for the function. It's an accumulation function. G of x is this thing. This is a weird accumulation function because I'm pretty sure I can find the antiderivative of that. And do I need to? Maybe. All right, so to write the equation of tangent line, I'm going to need to know a point that's on the curve, right? So we need to know g of 1. So g of 1 is the integral from 1 to 1. So that's good because it doesn't matter what I'm writing right now, because the integral from 1 to 1 of anything is going to be 0. So g of 1 is 0. So the point 1, 0 is on the curve. And now we're looking for the tangent line there. So we're going to need to know g prime. All right, so g prime. It's an accumulation function, the derivative of an accumulation function. We're going to take the upper bound and we're going to sub it in everywhere in the, I'm actually going to erase this. Okay, so everywhere we see, here's our integrand is really 1 over t squared plus 1. We're going to take the upper bound and sub it in. So everywhere we see a t in the integrand, we replace it. So it's going to be 1 over an x squared plus 1 times the derivative of the upper bound, which is 1, but I pretty much always write it when I'm doing these because I don't want to forget the chain rule when the derivative is not 1. So, and it doesn't hurt anyone to just write times 1. So I do that all the time so that I don't forget when I'm, when it's not 1. If the upper bound was like sine of x, we would have had 1 over sine squared of x plus 1 times the derivative of sine of x, which is cosine of x. You can't forget the chain rule. So that's why I write the times 1. You don't have to, but I think it's a good idea. All right, so g prime of 1 is going to be 1 over 1 plus 1, so 1 over 2. So then our tangent line, which I think you should label, is going to be y minus the y value that we got, which was 0, equals the slope that we got, which is 1/2, and then x minus the x coordinate we're using. So there you go. I think that is our answer. Let's try to find the equation of the tangent line when x is radical 3. So that's really annoying because radical, like you don't get 0. So we're going to actually have to do something to find g of radical 3. But that's okay because I think we know how to integrate this. So we have to do this. Okay, I prefer this integrand to look like this. 1 to radical 3. You might be in the camp that doesn't like the dt to be in the numerator, in which case, go for it. So maybe you like this better. Well, I recognize that. This is one where if you don't recognize it, you're in trouble. And so here, that's the derivative of arctan. So I know that the antiderivative will be arctan of t, and we're going to go from 1 to root 3. Okay, so now it's going to test our knowledge of, I don't know, the unit circle and things we have memorized. So we need to do the arctan of root 3 minus the arctan of 1. So this comes down to like, do you have it memorized? Hopefully you do. The arctan of root 3 I know is pi over 3. And the arctan of 1 I know is pi over 4. So what is that? 4 minus 3 over 12. So pi over 12. So that's the y value. That's when x is equal to root 3, the point on this curve is at root 3 comma pi over 12, which is like pretty weird for an ordered pair. But like, we don't really get to make that call. So g prime of x we found in the previous problem was just 1 over, right, is 1 plus x squared. I do that because it looks like the derivative of arctan, which is good. It also kind of looks like the sum of an infinite geometric series, which doesn't really matter to us. Oh, look at that. The next problem, the upper bound is sine of x. That's like the example that I gave before. So it doesn't matter right now that that's related to the sum of an infinite geometric series, but at some point in your life it will matter. And then I don't know if you'll thank me, but it's nice that you will have occasionally thought about it in the intervening years between when you first learned it and when you next encounter it. All right, let's write our tangent line. Tangent line y minus pi over 12 is, the slope is 1/4, and x minus radical 3. Okay, so that's our tangent line. Is it useful? I don't really think so, because if you gave me any x value to plug in there, I would not know the value that I get back out, because there's a pi in there, there's a radical 3 in there. So we did it, right? At x equals root 3, the curve and the tangent line share a value. They have the same slope. So we did it. It's just not like a super useful tangent line, but that's okay, because the problem didn't say make a super useful tangent line. So let's see if we can do this. So we need to find g of pi over 2. This is like same basic question, I guess. So g of pi over 2 is going to be the integral from 1 to the sine of pi over 2, which that's a good thing, because if you know the sine of pi over 2, you know that that's 1 from 1 to 1, which means we're just going to get 0 there. So that's good. So g prime is a little different this time, right? So you always want to go back and think, like, how do we find g prime? Well, g prime of x is going to be the integrand where every t that we see is replaced with the upper bound, with sine of x there. So it's going to be 1 over sine squared of x plus 1 times the derivative of the upper bound, which is the derivative of sine, which is cosine. Okay, so that means that g prime of pi over 2 is going to be, this one's kind of interesting. So it's 1 over, the sine of pi over 2 is 1 squared plus 1. The cosine of pi over 2 is 0. So it turns out that this tangent line is actually horizontal. And not only is it horizontal, it's just the x-axis, I think, right? So our tangent line, because the y value is 0, so y minus 0 equals 0, x minus, am I out of space? I am. Let me move this. Let's go over here. So our I should probably put it lower. Let's go here. Excuse me. So we get there. Still trying to write with the lasso tool. There we go. All right, but this, ordinarily I don't simplify these. This one you should really simplify. So it's actually y equals 0, which is really interesting. So I don't know how long the next problem is going to take, so I'm actually just going to wrap this up here. I'll come back in the next video and we will keep going on this page. So I will see you there.